Maybe this is the first presentation from this session that will not have the words vortex-induced vibration, so I'm sorry to disappoint some of you who were expecting mostly presentations about that. I guess the title of our paper is not very fully descriptive of what we're really wanting to talk about. As mentioned, I co-authored this with Professor Kamura, both from Tokyo Polytechnic University. But really what I'm going to talk about is the amplitude dependency of structural damping due to stick-slip friction surfaces in buildings under wind loading. So, damping. Actually in the previous three presentations, so they mentioned damping. So basically it's said to be one of the most important parameters in wind engineering. We need a good estimate of damping to get a good estimate of, let's say, building response to wind loads. One other application is, I've read some people, let's say, measure total damping in full scale. They make an assumption of that structural damping is constant. They subtract that from the total damping they measured and assume that the remainder is aerodynamic damping. So, in that, just one example, there's the accuracy of the aerodynamic damping estimate depends on the accuracy of the structural damping estimate. So anyway, for now we're just talking about structural damping. So as I've also mentioned, basically we've observed from many full-scale measurements, even from years back, we've observed damping to be amplitude dependent. Basically, it's damping has been. We've seen damping to behave non-linearly, even within the linear elastic range of, let's say, the main structure. And basically, when we say within the linear elastic range of the main structure, that's where, when we do, most wind resistant design, particularly for buildings, we would like the main structural frames to stay linear. And yet, as I've said, we've still observed non-linearity in the damping. And it is, I think many have said that the governing mechanism for the amplitude dependency of, let's say, structural damping in buildings is said to be stick-slip friction at contact surfaces. So let's say you have, let's say we have main structural frames, we have secondary elements, and then like partition walls or ceilings, cladding, even secondary structural elements, they will be in contact with the main frame elements, and then there will be friction at those surfaces, and more specifically, stick-slip friction. Now, based on that assumed governing mechanism, and of course also based on, as I said, there's plenty of full-scale data, the current damping predictor models we have are in this general format. So this is for a given building. Graphically, it looks like this, and they all basically suggest that damping increases with amplitude, x by the way is amplitude, and then reaches a maximum level at a certain point, and then it stays constant at that value. But we've observed from a few measurements at when the measurements were done at higher amplitudes, we observed damping to actually decrease with amplitude. So, I mean, initially it increases, but it also decreases with amplitude. And this is just one example that, I think it's very clear. And that's basically the motivation for the work we're doing. Measurements of damping are at relatively very low amplitudes. And then, meanwhile, let's say when we talk about occupant comfort limits, they're probably an order of magnitude higher. When we're talking about strength design for wind, they're about two or three orders of magnitude higher. But these measurements of damping have been, are what we use to, let's say, predict or damping for our wind design cases, which are, again, at higher amplitudes. So now I'll talk about the kind of modeling we did. It's nothing very new, but basically we started first with numerical stuff, finite element modeling, stuff like that. But schematically, it looks like this. So let's say we have a frame. Let's say this is a 1 degree of freedom frame, a mass stiffness damping. So this is the typical equation we find for free vibration in textbooks. And let's say there's a non-structural element of a certain stiffness, let's say K naught. And if that element is not in contact with the mainframe element, this equation still holds. But when it is in contact with the mainframe element, particularly when the building, let's say the structure starts to move, friction forces are developed at that contact surface. And the friction force developed there, basically it's less than what, well, I call this friction capacity. It's the friction that we studied or learned first in the first physics course maybe we've taken. And this is when the amplitude is small enough, let's say it's less than this value d sub c, related to QC and K naught, I call that the slip trigger displacement. Basically, yeah, and anyway, what was that? Anyway, yeah, the stiffness of the non-structural component is what do we call this? Mobilized, basically, and what happens is it suddenly becomes part of the system, of the whole structural system. And then when the amplitude of motion increases such that it's greater than dc, slipping starts to occur at the friction surface, and then the equation again changes. So there's that kind of non-linearity. And so I'm jumping here, but we've done numerical experiments that has sort of, basically numerical experiments that has sort of guided us to these theoretical expressions. We found that damping, let's say structural damping, so let's say this is, we call this baseline damping, baseline structural damping, it's constant. It could be taken as 0 if you want. But the amplitude dependent part, so it's a function of those parameters. Basically these are ratios, so non-dimensional the trigger displacement divided by amplitude. And also the ratio of the stiffness of the non-structural component to the stiffness of the bare structure. Likewise, for frequency, so it's also, of course, amplitude dependent. Those same parameters come into play. We can express damping as a function of frequency and displacements, which is quite convenient because that's the kind of things we measure. We can actually measure, more or less. I've been talking about just one stick-slip surface, one stick-slip component, but we know, or we don't really know how many there are in actual structures, so let's consider multiple stick-slip surfaces. And what happens to the theoretical expressions is that we just add a summation sign and some subscripts, and then another parameter is introduced, which is n, the number of stick-slip surfaces. And now, basically, the problem is it's difficult to determine the friction at all surfaces. We don't even know where all friction surfaces are in actual structures. So we consider those parameters, the stick-slip parameters, as random variables. We did a number of cases with different parameters. Essentially, we did parametric analysis, different numbers of stick-slip surfaces, different levels of coefficient of variation, different probability distribution types, both univariate and multivariate, and a number of different sub-cases. And, well, I could have shown you maybe all the results. It's in a video format, but I did not upload the video files anymore because anyway. So I'll just show you with a few examples. But basically, we could do a lot of, we could make a lot of conclusions from what we've done. But I would just like to leave with you just one thing. So this is, let's say, for one analysis run. I would like you to just look at this middle graph. So this is amplitude versus damping ratio. And in all of our runs, so of course, as I said, we've only covered basically these cases, these distribution types, and so on. In all of our runs, damping, we found damping, it increases with amplitude, but eventually it decreases with amplitude. And there are some cases such as this that, for maybe one order of magnitude is another one. For maybe one order of magnitude, the damping would appear, or we can consider it as practically constant. But again, but eventually it decreases with amplitude. And these are some of the even some few examples. Here we have very high coefficients of variation already. Damping, maybe it could, let's say, stay constant for maybe 2 orders of magnitude, but again, eventually goes down with amplitude. And actually, this is not a very realistic case, but we just added it in there to just cover everything. But this occurs only for when the friction forces at all surfaces are constant, which is, well, again, we don't really know that, but anyway. So that's just the one thing we'd like to leave you with, or at least from what we've done so far. This is just numerical stuff and theoretical derivations. Basically, we think that there's a strong likelihood that damping values corresponding to wind design level amplitudes could be lower than the largest damping values that we've measured, which are, again, at very low, relatively very low amplitudes. And that's my presentation. Just to mention, that's the first part of what we're doing. We have basically some laboratory scale experiments to do, and of course we have to take a look at full scale data and see how applicable what we've derived so far to actual full scale structures. That's our presentation. Thank you.
Thank you. There is some question.
I've got a question.
I think that there are other influencing factors such as locking of the non-structural walls, and then other connection material yieldings. So how you?
Yeah. So for now we're as I said, we've started, let's say, damping estimation started from the assumption of just purely stick-slip friction surfaces. That could, of course, occur also in actual structures. But for now, we're starting from that. I think we have to do a few things related to just stick-slip friction, and maybe later on, someone could do something about that.
Thank you. Another question from.
My question from the practical side of things, where does the micro-cracked concrete fit into this whole slip stick? Where in the relationship, or is it another lot of physics that we've got?
Yeah, so basically here I've assumed that the main structure stays linear, so maybe it's more applicable only to steel structures, for example, steel fully welded structures. And we're just assuming that stick-slip friction here comes from, again, non-structural components in contact with the main structural components. So, I mean, that's, maybe it could be applied, the same principle to, let's say, concrete, which compared to steel goes, basically there's a little bit of nonlinearity earlier at lower amplitudes. So maybe that could be done, but for now we're just saying, maybe the applicability is only to steel staying linear, in the linear range.
Any other questions? So we thank you again.
Thank you.